change happen. So you have a reasonable schedule that at least says what are the timetable and etc. But we need to make some adjustments. So I'm not talking about the change regarding the boat trip. It's also probable that will happen. But remember that yesterday we have announced that today's schedule is a little bit different from what was written there. And probably already recognizes that we started different. So just for an update, it's in the website. There is the best source of information. I hope we will not be hacked and this would be not true anymore. But in the moment, that's the best source of info. And as you have seen, we already had Fernando. We will have Nadja, second lecture now. And in the afternoon, we start with Fernando again. And as I have announced yesterday, Fernando is available for discussion up to today. Go to him in case you want to. Do not wake up tomorrow and say, oh, I would like to have a chat with Fernando, because this will not happen this time anymore. On the other hand, Nadja will stay here up until the workshop, so this does not mean do not talk to Nadja today. It's only mean talk to Nadja every day. And please, Nadja, get the continuation of your fantastic course.
Thank you, Marcelo. So, I wanted to start going through again the things that we did last lecture. So we were talking about maps and master equations. I want to give some references because I just gave the general references about non-Markovianity in these reviews. And if you're just really into maps and the properties of maps, typical maps, and all these quantities, I really recommend these two papers. One is by Kruszyński. It's really like the notes that he gave a course about time local generators, more or less master equations and maps. So it's really good. So Kruszyński is doing a lot in the open quantum system dynamics. And also there is this, there is this book from Benson and Zikowski with Geometry of Quantum States, an introduction to quantum entanglement. So this is also really nice, like really formal, but if you really want to like get a good idea of the formalism, I really recommend this book. And then Diogo was telling me that in the last 2 years, Lindblad and Kosarkovsky, they passed away, and they made kind of tribute to them, and there are these two papers telling their stories and also telling a little bit about this master equation story. So there is this in memoriam for Goran Lindblad, which is an archive paper from this year. So he passed away in November last year. And for Kosarkovsky, this was Kruszyński that wrote. For Lindblad was Bengtsson. And this paper published in 2021. Okay, just it's kind of the historical part of it. Okay, but it's nice. It's nice to read it and see how people are getting to these equations. Oh, okay, we already have questions.
Sorry, because you mentioned the geometry of quantum states. I have a general question on this since I come from quantum optics background. When I work with like entropy and entanglement, and sometimes I want to like read more into like what condensed matter like community wants to talk about entanglement, but I feel like it's very difficult to grasp. Is there like something you can maybe comment on this?
Like a good review paper of entanglement, but more like directed to matter physics, like
or like to what degree do you think like they're shared very much like a similar discourse between condensed matter and quantum optics?
Okay, about entanglement, I'm not the expert. Maybe Marcelo can give some reference. About the non-Markovianity, it's this second review that I told you from Vegas and Afonso. Because they connect with the experiments, and they are not really worried about quantum information. They are really worried about physics, what is happening in the physics of the, so this I recommend if you want to. I think it's a good, like, less quantum information, more quantum. Diogo has some.
About the entanglement, there is a very good course from Paraty 2019 that is available on our YouTube channel by Yelena Gurianova, so I recommend that.
Cool. Okay. So then, just what we saw in the lecture yesterday was we defined what is a Markovian and a non-Markovian dynamics. So we defined the Markovian as a divisible map, and we were motivated like to connect this Markovian definition in classical stochastic process. So if I have a map that is always divisible, and this is for all t and s, it's not just for two specific time points. So we know this guy has to be completely positive and trace preserving, and this guy also has to be completely positive and trace preserving. And if the map is non-divisible, which means it has a structure which is more like this, and to just make this differentiation between non-CP and CP, here I'm representing with a phi, and when I don't know if the map is CP or non-CP, I just represent with another level, okay, which is the V in my case. So the non-Markovian, I can try to divide this map, but what I find is that there is this intermediate map will be then, either it will be positive or not even positive. So it's not completely positive at all, but it can be that it is positive in some extension. Okay, we will talk more about this. So then to really understand what is the advantage of working in one regime or the other, I will going to check first, how can I identify if a map is CP or not? Okay, imagine you come to me and say, okay, I have this map here, can you tell me if this is a physical process or not? If you don't know anything about, like, you haven't been in the lab, you just have your Krauss operators, and is it a physical process? So then the question that we want to start answering is, how do we know that a map is CP? So again, I will define what is the space that I'm looking into. So I will start, before I was looking to states or density matrices that they were acting in a Hilbert space with dimension D. And now, because of this completely positive, you were always looking to an extended dimension. So I will now look to things that are living in this, just let me just see, larger Hilbert space, okay? DD. And I know that the map is completely positive if this extended map, which is identity in one part and the map in the other part, is just positive. Okay, I will say positive same definite. When I say positive, usually the zero is together, okay? So just allow me to say just positive. Okay, I can also think about another set, which are the states which live or act in a smaller extension, where here n is smaller than d. Okay? And then I say that this map, that's why I said there is a difference between completely positive, but it can be positive in some extension, and that's what I mean. It can be, I would say, n positive. If I have this, so identity acting on this system with dimension n, oops. The map is just the map that I had, if this is positive. Okay? Is it clear? It's just that the size of the dimension that I'm changing here. So, how do I know if I have a completely positive, n positive, non-positive at all? And this seems like, oh, this is just boring. But this makes a big difference about backflows, and like there are practical differences when I look to these different regimes, okay? So that's why I really have to go into it. But for answer this, like how do we know that a map is completely positive, I will have to explain some isomorphism, which is usually called the Choi-Yarmoukovsky. And in fact, we just, as in the Lindblad equation that we put all the authors together and we say that's the same equation, the Choi-Yarmoukovsky isomorphism are in fact two isomorphisms that they are kind of, they are equivalent, but they were like presented in very different ways. But okay, this is just some subtlety. But I will call it the same thing, okay? And what will we do in here? Well, we want to know what is the action of the map in some state that I will represent like this. And I can then represent the action of the map just looking, okay, this is are just the terms of like the representation of the density matrix. I hope this is clear for everybody, but I think so. No? I'm just defining a basis, and this is the element, each element of the matrix. So the map can be seen as just the action of the map in each element. Okay? So what I'm then what with this Choi-Yarmoukovsky isomorphism, what I can find is a different representation of the map. So then, from here, you can find that the map can be represented, and then here is the trick. I need two spaces, A and B. So, because I will connect, remember that it's completely positive. Positive is always, I will need some other space to be able to say if the state in this bigger space is still positive or not. So that's why here I also need a different space. So rho is just living in this A space and B in the B space, and where this tau has some information about the state, the map. So let's be, I will go slowly here. So what I'm finding here is a different representation of the map. And here's a so here is just the transpose of the state, the initial state. Here is identity. One is acting on A, the other is acting on B. Here is a matrix which has this form here. Well, it's just the map, like a larger map, acting on some state, and this state is the entangled state. So I'm not proving it, but I'm just telling you how is this, how can we do it. So this is a maximum. But it's apart from the normalization, okay? That's why this tau is not a state because it's not normalized, okay? And this tau state we call it Choi matrix. Many errors, oh sorry. Choi matrix or dynamical matrix. So what we see here is that if I know the map, I can find the Choi matrix, and using the Choi matrix, I can then find just the evolution, okay? So the Choi matrix, yes, there is a question. The Choi matrix contains all the information about the map. So with the Choi matrix, I can find the cross operators, I can find everything that I need to say what is the map.
Yes, I have a question because I don't get why the state has to be not normalized. Couldn't you absorb the normalization concept into the map?
Because let me see if I will do this. Well, I will, maybe this is not the right answer, but I will prove that if I choose this, it works. So if I had the normalization, I would have to take the normalization out at the end. So that's why it's not needed, okay? But maybe this is not the best answer for it. Okay. Cool. So before I talk, because why I'm defining this, the dynamical matrix is like very important to, it's kind of the first step. If I want to test if the map is CP or not, I just look to the dynamical matrix, okay? And I will tell you how. But before I do this, I just want to show that these two representations, this and it's not very easy. This and this, they are equivalent. Okay? So then let's do it. So I just have to define the dynamical matrix or Tron matrix, and it will apply for this Maximilian entanglement state. Well, here I will represent it as a matrix. So it will be then just the map acting on the A part times identity acting on the B part. I'm doing something that is very, it's not good, but this cross is just a cat and a bra, okay? A bra and a cat. If it's the notation is confusing, just tell me that I will go slower to do this. But this is this, okay? The butterfly. Sometimes once my student was, what is this butterfly? And I said, it's just a cat and a bra together. Yes, there is a question. Yeah, sure. Let's see. Sorry, yeah, thanks. So then I will just replace this state. So as I said, we have this trace B, then I can replace it. A, J, B, and we had this identity times this state. It could be AJ, but just okay. B. And then this. Okay. So the partial trace you already saw it last time. I just have to choose a basis, and so it's just in the part B. This is already the partial trace, and I will do for this whole thing. And I get, okay, just reorganizing what is acting on A and what is acting on B. These things I do quite fast, but I hope that you believe, and if you have a doubt, you can just go and do it by yourself so that you are convinced that the things are correct. But it's just, I'm reordering the terms, okay? Here's again, the problem when you open up you have really to concentrate on these indexes. So here I'm just ordering the A part. And then I have the K, which is acting on the B part. See here, this is acting on this. okay? I'm just repeating it here, then it will come the J. Everybody. Then I have, well, the identity is acting on A, so it's already multiplying this, so that's why this is remaining. And then I have the B part, A, G. So let me just put them together. So is it clear what I did? Okay. So what it happens, okay, since I'm working with orthogonal states, when I multiply this K times I, so there will be some chromatic delta here. So delta Ki, and also here. And then we see that, okay, I has to be equal to K, and J prime has to be equal to K, so at the end, we have then that the only term that is resulting from all these trace, partial trace, is the J equals K equals I, and I prime equals J. So this is just AJ, rho AJ, phi, J. Ta-da! Okay? Well, if you were lost in my like letters or just go back and, but it's quite simple, this calculation, but I think it's important, okay? So I showed you that I have a representation with the dynamical matrix, which I'm calling this tau, and if I have the dynamical matrix, I can do just find the map or find the cross operators, and I know the quantum evolution of the state. Okay? Any doubt about it? Then I can use now, what I want is to use this theorem, which is called the Choi theorem, where they say that a map, phi, is CP if and only if the dynamical matrix is positive. Which means that this is the dynamical matrix. So if I want to check if the map is positive or completely positive, I just calculate the dynamical matrix, check for the eigenvalues. If the eigenvalues are positive or zero, fine, the map is completely positive. Problem solved. Because what does it happen? If I don't know, what usually I have is this intermediate map here, and then I will have to check this intermediate map here. Okay? So sometimes I just have the evolution from 0 to S, the evolution from 0 to T. So by hand, I can calculate what will be the intermediate map. And then I'll have to find if this intermediate map is CP or not, and then I can tell you if it's non-Markovian or Markovian. Okay? However, to find this dynamical matrix, you already need to know what is the map. Maybe you don't know what is the intermediate map, and this is something you have to do after you have the map, like from 0 to S and 0 to T, but you need the map. And as I said, to find the map in the lab, you have to do this process tomography, which is not experimentally so easy to do. So are there other ways to verify if the dynamics is Markovian or non-Markovian? So this is our second question today. Or verify in a way who also or witness. What do you think? Or what you have heard about? Yes? No? How? Any guess? No? Come on, people. Let's get awake. Yes, but we say yes. Cool. How? How do you know we can verify or witness non-Markovianity without looking at the dynamical matrix? No idea. Never heard about it. Okay. Well, we know that there are quantities that they are just monotonically decreasing under a completely positive map. So, what we will explore here is what we call this backflow of information, and I will explain better this, okay? But this is essential to the things that we'll be doing here. So I had my scenario, my system, in contact with some environment, and what we notice is that there are quantities that when my system is evolving, you are just losing information to the environment, but if the dynamics is non-Markovian, there will be some quantities that, like the information go back, and I will say this recover of information. I already told you this in the last lecture about distinguishability. It was quite fast, so it's okay that you couldn't connect to this to the end of the other lecture. But do you remember, I started with state 0, I evolved it, and it went to the identity, and then state 0 again. And if I start with the orthogonal state, it was 1, identity, 1 again. So I had this recover of distinguishability. And these are the things we will explore here. We explore any function that present a monotonic decay in time, under a CP map. What I mean is that I need a function that the evolution, the evolved state, the function evaluated in this evolved state is smaller or equal to the function evaluated at the beginning, okay? And this has to be for all times. Well, the distinguishability, if we just think about what is happening like usually in the blocksphere, if we are evolving, it can be, like, let's think about the depolarizing map. The depolarizing map is just shrinking the block ball. Okay? You are going, at the end, the completely depolarized state is just a mixed state. If you think about the light, if it's a completely depolarized light, you just have like polarization, the light will be polarized in no directions. The light that's coming here from the source, from the common lamp, is just something that is like polarized in all directions, okay? So this is just represented by the maximum mixed state. You have a probability to have a state in any direction, equally, okay? So the depolarizing map, I have the block sphere just shrinking to the point inside the block sphere. So if something does with the block sphere kind of this, so then this will be a sign of a backflow, okay? So usually the map is just shrinking, but it can be that it makes kind of this contraction and expansion. And this is what we will explore here. So the first function that we will look at is the trace norm. And you will see that the trace norm or the norm 1 is the same thing. They are connected to distinguishability. So how the norm 1 for any operator is just defined as square root. And one other way to see is just the sum of the absolute value of the eigenvalues of delta, okay? And then I will explore a theorem. I'm not proving it, but let me say if I'm not proving, I'm proving it, okay? Well, it will be more proof than I thought about. So what I will see is that I trace preserving linear map phi is positive if and only if for any Hermitian operator. So it's more than the ACT operators, because like any Hermitian operator, I'm not imposing trace 1 and delta acting on the Hilbert space. So the norm 1 is just decreasing or staying equal. Okay? So if I have a positive map, to talk about completely positive, I just have to do this trick about extending the space, okay? But this is defined only like for positive map, but I can use it also to check complete positivity. But if I have a positive map, what will happen with the trace norm of all Hermitian operators is that the trace norm will get smaller. So, just to prove it, we have to divide it in two groups, this proof. Is it any question here about the theorem and its trace norm? Okay. So first we will assume that delta is Hermitian, but it's also positive. Okay? Because I just assumed that delta, the theorem is saying about for any Hermitian operator, but I haven't put any restriction. Now I'm assuming that delta is positive. So if delta is positive, and I'm just acting a map on a positive operator, so the final operator is also just positive. So then at the end, I would see that the trace norm is not changing. This is easy. Okay? So if delta is not positive, it's a Hermitian operator, but it has some negative eigenvalues, then I will separate it in the positive part and the negative part. But I will do in a smart way, in a way that this delta plus and delta minus are still positive operators. Is it clear? Because this is, let me can do this. These are the positive eigenvalues minus the absolute value, okay, is I, J. Yes? Are you convinced about this? Okay, then here, this is just a positive operator, so the minus sign is outside, okay? So then I can do now, calculate the trace norm of this evolved Hermitian operator, and this will be like the map applied to the positive part minus, I'm always talking about linear operators, so the action of the map in a sum is the sum of the action of the map in each part, okay? So this is, that's the thing I said. So usually we can just give up about completely positive, about linearity. It's no. Your life will get hell if you give up about linearity. We don't like giving up about linearity. So, and it's kind of a tricky question because we have no linear process, we have no linearity. But okay, this is for a next course, not for today. So then, if we just have the trace norm is a norm, so it fulfills this. We can use this inequality to say that the norm of the sum of two guys is just smaller or equal than the norm of each guy. Can explore this. And then we just know, okay, this is just the sum of the eigenvalues of the positive part. This is just the sum of the absolute eigenvalues of the negative part. So at the end, this will be just this part here. It just be equal. Oops, what is this? So then what I do have here is just and this is actually the result that I showed you before. Okay? So if the map is positive, so for any Hermitian operator, either the trace norm will remain the same, or the trace norm will just decrease. But it cannot increase. Okay? Any question? Yeah, cool. Then you can drink some water.
Well, it seems that the possibility to write delta as delta plus minus delta minus, right, is a very restrictive condition. You know, can you guarantee this equality for any
Hermitian operator is a Hermitian operator.
Hermitian? Okay.
Okay, this is important.
Because it seems that just a very little subset of operators
Well, let's
fulfill this condition.
put it like this. Any Hermitian operator can be diagonalized.
Yes.
Okay, so I think this everybody agrees about it, and it will have then real eigenvalues. They can be positive or negative. So I'm just separating into groups.
Oh, okay.
So the restriction is that I have Hermitian operators, but this is not so bad for us because in all the observers are Hermitian operators, so it's fine.
Yeah, the point is that this is much simpler than I thought. So that's it. Thank you.
Yeah, it's important to have the Hermitian operators.
Yeah. Okay.
Okay.
Hello. Can we relate the result of positivity with quantum correlations? Because when we apply local operations to a system, the entanglement decreases, right? Then we can only define positivity looking only for the quantum correlation, or no?
Yes, we can. We will get there. I will talk about it. Okay? Thanks for the question. So, then, okay, I'm talking about. Sorry.
Yeah, so
Isadora.
is this the full proof, or is it just one way of the proof?
It's
It's that if and only if thing, right?
sorry, yes, you're right. I just did one way.
Is it clear why the other way also holds, or something a bit
It
more?
holds. It's a little bit, yeah, it's a little bit more work, but just the one way. But it's even only if it's both ways.
Okay.
Okay, yeah, thanks. I like this audience. They don't do them all the points. It's true, I did just one part. Okay. So these are the theory. I'm talking about positivity. But at the end of the course, you will be like, I cannot hear this anymore. But it's just how these things are connected. If then I want to check if the intermediate map is CP. It's just, I have to check if this guy here is P. Do you agree with me? So what I have to find is that I can just explore this theory, where here my Hermitian operators, they are acting on the space of these sides here, okay? So if I'm able to check all the Hermitian operators and the trace norm is just decreasing, well, I can tell you the map is completely positive. Okay? This is not very practical because I have to check all the Hermitian operators acting on DD, Hilbert space size D times Hilbert space size D. But the good thing is that if by luck, I find one Hermitian operator where the trace norm is not decreasing, I can tell you already that's non-Markovian. So you need at least one example, and then it's fine, because that has to be for all Hermitian operators. So if you are lucky enough to get one example where you see this increase, so you can tell, you say, you know that VT is non-CP. Or, yeah, not completely positive, sorry. So there is at least one delta where the norm 1 increases. In time. Okay? So, cool. But while we are talking about emission operators, and while this kind of, it seems like difficult because there are many emission operators, so how can I find these emission operators? So one thing is that, another thing that I can do is, I can connect this emission operator to density operators. And then things start to get more similar to what we did in the last lecture. So I can see that delta can be written as, I have two states, rho 1 and rho 2, and I can just construct any emission operator as, I won't say convex sum because I have a minus sign on here, but there's this sum of two density operators. And then what I can see is that if I choose this Q equals to 1/2, this delta will be connected to distinguishability. And then, okay, this is one of the first witnesses of non-Markovianity, distinguishability of states. It will be clear in some seconds. Which is, okay, I choose Q equals to 1/2, so delta will be rho 1 minus rho 2, and then this is just the definition of distinguishability, which is the trace norm of rho 1 minus rho 2 divided by 2. And then, okay, I will use the same result as before. So we know if the map is known, completely positive, there will be a emission operator there where I see this increase. Maybe you are lucky enough and your emission operator is just this guy with Q equals to 1/2. And then you will see this looking to the distinguishability of states. I already gave you an example in the first lecture where the distinguishability is increasing. Okay? So, and that's why they were exploring in this paper, where they show that the distinguishability is a witness of non-Markovianity. So at the end, what they see, but what they are exploring is really this Choi theory about positive maps. Okay? Like, if the evolved distinguishability for these two states is just getting smaller, so I will put some other time here, T and S, and I'm assuming that S is smaller than, S is smaller than T. For all T is 0, I would, well, usually I would identify with this Markovian, and otherwise, non-Markovian. But wait, we have to be careful here, because this, maybe you were not lucky enough and your emission operator that gives you the backflow is not the one with Q equals 1/2. So the fact is that when I have the distinguishability that's just decreasing, I cannot tell you much. It can be still non-Markovian. The only thing that I really know is that if the distinguishability is increasing, then I'm sure that, okay, this is a non-Markovian dynamics. Okay.
Hi, Nadja. So just to confirm, when you have a non-Markovian process, you always have backflow of information. or not?
Yes, but not
Oh.
if I'm just okay. I have a backflow of let's go back to the choice theorem. If the map is positive, I always have for all emission operators the trace norm is just decreasing. So for non-Markovianity, what I'm checking is if the intermediate map is completely positive.
Okay.
So to use this choice theorem about positivity, I have to go to a extended space. So if I'm in the extended space, yes, I always see backflow of information. If I'm just as here, I'm not in the extended space, I'm just Hilbert space D, then it's not true that I will always see backflow of information. Okay?
Okay, thank you.
And this is a very good question. It was the sentence I was about to write. So, not all non-Markovian dynamics present an increase of distinguishability in these terms here, okay? This is important. So, is there any other measurement or witness connected to this choice theory that always detect or always witness a backflow of information? And yes, there is. There is something I did. Okay, sorry, I had to cite the people that did this. And also because people just in the community just say VLP witness or quantity. So the guys are Breuer, Lane, which was already a student here in Paraty, Elsie, and Pilo, and Isabel. People call it Bell LP criteria. It's a pure L. From 2009. So there is this other result where this choice theorem is connected to another quantity which is not distinguishability, but is the guessing probability. And what is the guessing probability? So, and this was like a result after the VLP and all this discussion, when does the non-Markovian dynamics have a backflow or not, blah, 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 blah. So they find these two guys, Buscemi and Ilanjan data. They show that yes, we always have backflow of information, but you have to go to this extended space, and they started it thinking about this guessing probability, which is, imagine that I have the following game. I have a quantum system, I know the dimension of this quantum system, and I can produce, or I can just prepare it with some probability with some probability Q, I will prepare it in state rho 1, and with some probability, complementary probability, 1 minus Q, I will prepare in state rho 2. Okay? And then I will send you this quantum system, and like I'm preparing here, I'm not telling you in which one of them I'm preparing, but you know I have possibility Q1 and Q2, okay? And then with just one measurement, you have to guess if it's rho 1 or rho 2. Okay, so that's why this guessing. So I would say Alice is preparing here and Bob has to guess. So this is the game. And then, well, if it's just two orthogonal states, it's easy. Imagine that it's just Alice is preparing 0 or 1. What will be the measurement that Bob has to do to guess if it's 0 or 1? Huh? Nina?
And he's going to measure the computational basis.
Yeah, Z or sigma Z. As Richard was telling us many times yesterday, sigma Z. Okay? If they are orthogonal, it's easy. But the thing is that they don't have to be orthogonal. Okay? So the game is quite general. So what we know, they will have to do some measurements, and they don't even have to be projective measurements, they can be more general measurements. So there will be a set of these positive operator valued measures, which are the more general representation of a measure. And what will happen is that they have a set of possible results that they will say is row 1. Connected to row 1. And the complementary set is just connected to identifying row 2. Okay? They always will give you, they have to say row 1 or row 2. They cannot say, I don't know. Okay? This is kind of a small restriction. They will have to tell, okay? They can even, randomly guess if they don't have any smart strategy. But as they know who is row 1 and row 2, as I said, if they know that it's 0 and 1, they just know that they have to measure Z or sigma Z, and they will be always able to tell you what was the state. Okay? So then we can calculate with this, the set is just T, is the sum of all these operators with the, like, I would say if it's 0 connected to the result 1, and if it's 1 connected to the result -1, and the other set is just the complementary of it, associated with row 2, okay? So then I can calculate the guessing, the error probability, which is, imagine that I measured one of these operators here that normally is associated with row 2, but somehow there was an error and I said it's row 1. Okay? Something went wrong and I thought it was row 2, it should be row 2, but I associated with row 1. So I have this error because if they are not orthogonal, there is always a probability that I will measure something that I think there is kind of a projection in the part that I don't want, okay? So we can then calculate a guessing error probability, and this error probability, I'm minimizing it, so I want to find what's the best positive POVM sets, which minimize this error probability. But at the end, what I have is that, okay, imagine I'm measuring T and I'm associating with row 2, and I'm measuring 1 minus T and I'm associating with row 1. So this will be like the errors, okay? And then what we can show, and I'm not doing this, is that this is connected to the trace norm. And this is very nice. It took me a while to understand these results from there. In this paper. To the trace norm of this delta operator, which is just constructed in this way here. So see, I was talking about Hermitian operators. Now I'm already connecting to this game. I'm already connecting the trace norm of this Hermitian operator to a guessing probability. So in the same way that I use choice theory and I convinced you that if the map is not positive, there will be a Hermitian operator that is increasing in time. So there will be then, if I have this delta, I can connect it to this guessing game, and there will be a situation or a set of states with probability Q and minus Q, where this guessing probability will increase in time. But the only thing that we have to be careful here is that if we want to use this positiveness connected to complete positiveness, this guy is in this larger Cubic space. Okay? So you said, but why you don't just extended the distinguishability definition for a larger Hilbert space? Because the distinguishability definition is just to Q equals to 1/2. And here I wanted to be general because it can be that I wasn't lucky enough and my Hessian operator is not the one connected to Q equals to 1/2. Okay? And they wanted to give a physical motivation for it because distinguishability we understand. But just to say the trace norm of our Hessian operator is increasing, what does it tell me? If I'm thinking about quantum information protocols, I want to use it for something. Okay, I have here a clear motivation, I have this guessing probability, I have this game where I want to guess things, and it seems stupid, but this is connected to many protocols, okay? The ability of guessing a state, just preparing some set of states and be able to guess it, okay? Even if you think VB84 already gives you something you are preparing two different bases, and Bob is measuring other bases. Imagine that Eve can guess which state Alice has prepared. So things like this, just to give you a little bit of the feeling. So that's why we are looking to guessing probabilities, but these things are connected. Distinguishability and guess probability, they are all getting advantage of this choice theory that I presented at the beginning. Any question, guys? Yes.
Probably a very silly question. Row 1 and row 2 that, you said delta equals Q row 1 minus 1 minus Q row 2, right? And row 1 and row 2 are density matrices.
Mm-hmm.
So their trace is 1.
Yes, this is a Hessian operator with trace 0.
Q is a number between 0 and 1.
Yes, this is true. Sorry, I haven't said it.
So if you take the trace on both sides, so the right-hand side you're going to have minus 1, right? If you calculate the trace. Because the trace is linear, and so Q...
it's 2Q, sorry, no, it's not 0.
Oh, okay. All right, yeah. Okay, now it's clearer, much clearer. Thank you.
Sorry, no, it's not trace 0, because if it's trace 0, the trace norm is just 0. Sorry.
Hello. So this is exactly quantum state discrimination. I was thinking, because we use minimum error discrimination here.
Mm-hmm.
Does something interesting happen if one were to use another scheme of discrimination? For example, unambiguous discrimination.
Okay, the game is kind of I'm not thinking about different games. I'm sure that you can use, if you have more states, you can also think about different strategies. But they just wanted to convince you that there is at least one quantity that you can always see a backflow of information in terms of this quantity. But I'm sure there are others, okay? I can think about some other schemes, other discrimination, even more more efficient or more, I don't know.
Yes, so it was just a narrative device.
Hmm?
It was just a narrative device for the talk. Narrative device for the talk?
I cannot understand.
I'm saying that what you said, you did here, was a narrative device for the talk.
Mm-hmm.
Okay.
Yeah. Well, this is nice. We have something that we always recover, like this guessing probability. But to know what is the set, the ensemble where I have row 1 with probability Q and row 2 with probability 1 minus Q, is also not straightforward. So we were really excited about this result of Nadja data. Wow, okay, we always see backflow, but well, we know how to find this set of, this ensemble of states. And then people they are so smart that one result leads to the other, and they found a method to always find this ensemble of states. And I will not go through these results, but I have to mention because I think this is really nice. So a method to always find this ensemble was done, and they weren't able to do this for all maps, but all maps, for invertible maps, they can find a way, and this paper I really like it. Lika, which was also here in Paraty, Bogna, as a student of VIII. From 2017. Okay, so cool. We have backflow in terms of guessing probability. We know how to construct these states. So then, but can we think about other quantities? Because the guessing probability or the distinguishability, it's connected to some protocols, but we are always thinking also about correlations. And then this is not really like connected to correlations, not in a straightforward manner at least. So then this is connected to the question of Pablo? Pablo? No. I'm not finding him anymore. Okay. You, what's your name? The guy that asked for about correlations. Pedro, sorry. So he asked about correlation, so we can also see a backflow of information in terms of entanglement. Which is looking to backflow in a different perspective, and this is a result from Vivas, Helga, and Plínio. More or less at the same time of the distinguishability. And what they show is that, okay, I have my system, which is in contact with some environment, but imagine that I can explore some ancilla, and somehow the system is evolving because of the environment, and the ancilla can isolate it well, but the system, no, I cannot. Okay? And then I would check for entanglement between both of them. And what they showed in this paper, this is one of the results, they have two results, important results here, is that, and here is time. So if I just check for entanglement versus time, so Markovian dynamics, this quantity will just decrease in time. And there are no Markovian dynamics where I can see an increase in entanglement. So then the entanglement is decreasing, and at some point it will increase again. Okay? So then they will measure they will define this measurement by this, how much it is increasing. So this is the quantity that they are defining in this paper. Whoa, this is really cool, because we can then connect to all protocols that we use entanglement. We can think about, well, maybe I can do some engineering in the reservoir. If I cannot isolate this, maybe I can get some advantage about it. So I can think about non-Markovian dynamics. I will lose information, but at some point I can recover information. So instead of doing my protocol in this time, I will just wait a little bit and I will get more entanglement. So this is really nice. But as I said, this quantity is also not necessarily sufficient. So they are non-Markovian dynamics that they are not identified by entanglement in this form here. So I will talk. I still have 10 minutes, eh?
Yeah.
So, one lesson. I'm finished. So it doesn't work.
Hi Nadja, just a second, please.
Yes.
So this increase in entropy, in entanglement, can it ever surpass the initial entanglement?
No.
No, okay. So
No free lunch.
No, yeah. So like, it may be better to wait to
Yeah,
perform
imagine
measure,
you-
but if you can perform immediately, it's still better. Okay.
Okay, I think a very good way to think about it is imagine you have to send your entangled state, or at least one part of it. You are not doing these things on your lab, because if you are doing the lab, you just prepare the maximum entangled, you just work with it. But imagine you want to do something that is distant somehow. So you know that it will go through a fiber and it will suffer some decoherence in this fiber, and then maybe you can just wait a little bit more to do this, because you will lose entanglement, will recover a little bit, but not like you can get to the maximum to the beginning, but not more than in the beginning. Okay, so no free lunch. So, but maybe it's not time. Maybe just is this the length of the time is encoded in the length of your fiber. So instead of working with a fiber of 1 kilometer, you do like a 2 kilometers fiber. We are just presenting a result where we use this for like a quantum vault. So how we can store information using non-Markovian. So this will be presented in the workshop, but I think there is a poster. The multi-core fibers guys, students. No, he's not here. No, okay, but there will be a poster, okay? Okay, it doesn't identify all non-Markovian dynamics. One special example is, imagine that I have here my total evolution. It's just, I don't know why many guys here. My total evolution is just this guy, but the map is an entanglement breaking channel. So you can start with a maximally entangled state, and then it will just go to entanglement 0. So there is no way that you just with local operations you will make you will see a recovery of entanglement. So this is already an example where I don't see recovery of entanglement. But then there was also another result where they show that using more ancillas, so the trick is always going to a larger Hilbert space. You can always identify non-Markovianity with entanglement, but also just for invertible dynamics. So this is a kind of open question that we hope to have answered. We are finishing this paper where we show a way to always find a weakness to identify non-Markovian dynamics, not having this restriction of invertible maps. Okay? So this, I have to acknowledge the guys. Yannick was also a student here. Kolodisky. Which is a PRA from 2020. Rapid communication. This is like universal entanglement weakness. Okay. Yeah.
So you mentioned different methods to detect potentially different non-Markovian dynamics, but do they have specific applications, like the ones that are detected by entanglement, for example, or do they have different operational meanings about these non-Markovian?
Well, I can just maybe briefly say something that I wanted to prove, but for the entanglement, I haven't seen people showing like, I know this about the entanglement breaking channels, that if the channels are the entanglement breaking, for sure you won't see recover, but I don't know any results about where people show different channels where the entanglement is not recovering for non-Markovian dynamics. For the distinguishability, we know that the map, and this I will just mention because I was planning to show, but since of the time I will just mention, but the distinguishability, which is called the BOP criteria, it will be always witness non-Markovian if the intermediate map if this guy is non-CP or non-P. It's non-CP, of course, but it's non-positive. So there isn't any extension where this guy is positive. So this is what we call strong non-Markovian. So only these guys, they show a backflow of information in terms of distinguishability. Okay, this is something we can prove. So if the dynamics is non-Markovian, but it's non-Markovian and this intermediate map is N positive, it's not completely positive, but it's N positive, so I can show that I will never identify this non-Markovian with the distinguishability. But if it's a strong non-Markovian, I will always be able to find two states that they show a backflow. Okay, so this for the distinguishability we know. But for entanglement, I haven't seen it. I don't know if it's possible. Yeah, sure. Yeah, I decided already this, I won't go there, it will happen. So, okay, just answer the question.
Maybe, because I don't know much the motivation, but are all the non-Markovian maps useful? And then, or do you have such thing like PDT that you have for entanglement, and then depending on the criteria, maybe something is not useful anyway?
Yeah, this is good, because I was kind of not telling you this, but it's a good question, it's important. I showed you, as entanglement here, I showed you that there are situations where the recover appears, but there are situations with no Markovian that it gets even worse. It makes, the entanglement gets, decrease faster. So it's not straightforward that, I have no Markovian, yeah, I will have this, it's better. No, it depends. Okay? So, of course, if you are in the scenario of extended ancillas, then you will always be able to see, but also you have to know exactly the time, so it's more complicated. But if you just are in this scenario, system, on one ancilla, then it can be that the non-Markovian dynamics is doing is making the things worse. And that's why people at the beginning, they didn't want to have non-Markovian dynamics, because this is kind of correlations that from the environment that you don't know when this information is coming back, if this information is coming back. So it's difficult to treat it. Okay? Any other question?
Before you have used some Q or
Which part?
There key 1 minus 1 minus Q. This key can be related in time to.
No, this is related to the probability. Imagine your game is, I want to prepare my quantum system, and sometimes I will prepare with this in state 1 and sometimes in state 2. And this will happen with probability Q, if I'm preparing state 1. It's just related to the probability.
But we can somehow relate to, let's say, in the initial time you have a system and then be connected to the environment to...
Well, because, this is from the structure that we are thinking, the initial system, the map, and the evolved system. So everything that is connected to time, I'm putting in the map. So the initial system is time 0, okay? So that's how we are just separating things. But we could think about Q that is changing in time, but this will be the same as starting with a fixed state and acting with a map. Okay?
I really couldn't get yet what's the meaning of the ancilla, like what Brandão said, or is the physical meaning of the ancilla?
Yeah. Okay. Brandão is using an ancilla because he doesn't want to measure directly their qubits. So he wants to get some information about the error that happened in the qubits with the ancilas. Here it's kind of the ancilas, they are the part that they are not suffering the map. It's similar somehow because there, like the error is acting, but the ancila is getting some information about the error. Here it's just a way that, okay, mathematically it's easier to explain because I just want to explore this positive result, but I want to say something about completely positiveness, and that's why I use this ancilla, okay? But if you think about the physical situation, the map is just acting on the part of the system. The ancillas is nothing is happening there. They are just.
So there's no evolution on the ancilla?
Well, it depends. Like as here, when I talk about Schroy matrices, then the ancilla and the system they are maximally independent. But there is no evolution in the ancilla. Okay.
Further questions?
Okay, then.
I actually have one. So thinking in use of non-Markovian as a resource. So like there are these models of quantum computation where it's like dissipative. So you try to put the answer to your problem like in the asymptotic state of the dynamics. Is this related in any sense to some sort of non-Markovian?
As far as I know, because I'm starting to learn these things, all these models, they are for Markovian dynamics.
Okay.
So this is something I also want to explore, to understand. But I haven't seen any of these random walks like these models that, I don't know if they are not Markovian, they are Markovian.
Cool. Any final questions? Or if not, let's thank Nadja for the video.
The announcement guide once more. If you check the program of the school now, you see that we'll have the boat trip on Thursday. So be prepared for poster sessions today and tomorrow. And the Google Forms will be available soon. Choose your emails, the email you have used to make your enrollment here, okay? And please be advised that it has to be filled until noon tomorrow. And since noon tomorrow we'll be here having classes, pay attention to make it much before noon, please. Okay? I think this is okay, and cachaças will be available at some moment in the near future. In case anyone else wants to read the poster here, not to walk with it during a rainy day, just appear in the door behind the stage immediately, please. Anyone who wants to leave the poster here instead of walking with it.